Hello, welcome to the laser part of the course. In this course, we are going to look at the physics that underlies the functioning of a laser. As you know, the acronym LASER stands for light amplification through stimulated emission of radiation. And we know the applications of laser, which are too many to list. It is ubiquitous, it is there, it has been the part of our modern life for now about half a century. So the first laser were invented in 1960 by Myman. Now one would wonder that the underlying aspect of that of stimulated emission was discovered by Einstein all the way back in 1916. And it took nearly half a century to actually make a laser. So obviously there is a catch in it. So the catch was that the scientists had to figure out how to efficiently thermodynamically drive the atoms and extract energy from it. And that is something that we will hopefully put our fingers down to through in this course. So you see, in a laser, there is gain and there is tremendous amount of loss. And this careful balancing of loss and gain, right, it required us to understand the physics better. It's only when we understood that one could actually drive atoms in a gainful manner, in a thermodynamically efficient manner to extract. It is a device that is based on extremely strong interaction between the light and the atoms. One cannot ignore either aspect. One has to self-consistently describe both these entities in this strongly coupled regime. Now, if you look at the applications of lasers, they vary from very mundane things like the laser scanner in a supermarket to that of lasers required for surgery in medicine. There are very esoteric applications of lasers, which has made new physics accessible through experiments. For example, one can get the lowest temperatures in the universe by using laser cooling. This is the application of lasers where one can bring down a collection of atoms to a temperature which is close to 0 Kelvin, not really 0 Kelvin, but then it can be as little as 10 to the power of minus 9 of a Kelvin, this nano Kelvin. The same laser probably can be used to create energy densities which are extremely large. So large they are comparable to the energy densities inside the core of stars. So you see, from astronomy to very mundane applications down on Earth, which for example is reading an audio CD inside your computer, all of these have required laser as their central primary element. And it is this laser that we will try and understand. Lasers have a variety of, there are a variety of types. There are gas lasers, there are solid state lasers, there are liquid lasers. Lasers intrinsically require an interplay between variety of areas. So you will see it is truly an interdisciplinary venture to make a laser. The simplest of lasers require inputs from a physicist, electrical engineer, putting together cavities whose stability probability is determined by a mechanical engineer. And then you have lasers that depend on supersonic expansion of gases. Maybe you require an aerospace engineer to understand fluids of that kind. You require chemistry in chemical lasers. So there are these variety of expertise that you need to bring together to make a laser. So we will of course not dwell into any specific laser. We will look at a generic laser and try and understand the physics behind it.